next 6 minutes, our focus will lie on the energy, material, and resource efficiency. Also, you will learn about how the holistic life cycle management being applied to upcoming industrial processes and recycling technologies. We at the TU Braunschweig's Chair of Sustainable Manufacturing and Life Cycle Engineering have core competencies in the fields of sustainability in production and life cycle engineering. We have developed the concept of total life cycle management, which serves as framework for our research and education activities. At first, let us ask ourselves, what are these efficiencies? To begin with, material efficiency entails the pursuit of the technical and business strategies that would lead to a substantial reduction in the production of high-volume energy-intensive materials. Then what are energy-intensive materials? Energy intensity is simply the energy required to produce a material from its raw form. This production of raw materials is one of the main contributors to emissions and environmental impacts. Among the sources of annual industrial greenhouse gas (GHG) emissions, the production of 5 materials, namely steel, cement, paper, plastic, and aluminium, account for 55% of industrial emissions, commonly called as Big Five. In order to meet the present-day demand of goods, industries have also ramped up their production quantities. However, the adverse effects of this on the environment have also become evident. Environmental impacts like global warming and ozone layer depletion have become a major concern. In order to mitigate these impacts on the environment, innovative strategies and technological measures have to be employed. Out of the many viable options, one promising sustainable strategy is circular economy. The main focus of circular economy is to keep waste to an absolute minimum and reuse resources as long as possible. It also encompasses promoting and designing products that can be reused, repaired, and recycled. According to a study on global flow of plastics, 6 to 8% of global oil consumption is caused by plastics manufacturing, equivalent to the global aviation sector. Packaging alone is 2 to 3% and generates significant negative externalities. A very high percentage of the plastic either goes to incineration, landfill, or leakage in its end-of-life phase, causing pollution. This existing non-recyclability results in further requirements of virgin materials to keep up with the demand for plastics. Recycling of plastics is a viable option for plastics by minimizing incineration and landfilling. However, it is only feasible when emissions due to collection and reprocessing are significantly lower. Moreover, multiple aspects such as designing better products, encourage recycling and reuse, etc. need to be considered. Well-established recycling technologies such as mechanical recycling are already operating close to their limits. For emerging technologies such as chemical recycling of mixed plastic waste, the availability of data is a problem. But against this background, it is important to determine the environmental performance of new recycling technologies early in the development stage. For complete accountability, it is important to study the total life cycle for identifying the origin of emissions or hotspots, as a single measure aimed at reduction of emissions in a particular phase should not just shift the problem from one phase to another. Up until this point, we have mentioned that circular economy is a viable option and life cycle perspective is necessary. The next rational step is to define a methodology to quantify the emissions and prove the above mentioned. The framework defined in the ISO 14000 is a widely accepted standardized procedure as a life cycle assessment. Through life cycle impact assessment, linking life cycle elementary flows coming from a product system to environmental impacts is enabled, and it follows 4 major steps as shown. The life cycle impact assessment involves assigning the elementary flows from life cycle inventory to selected impact categories. The next step involves calculations concerning the chosen category indicator. Let us now consider an example for emerging recycling technology. In In the project iCAREPLAST, eco-efficient plastic upcycling with cyber-physical recycling system is being developed. Different energy-efficient process and technologies are being considered to upcycle plastic waste into useful virgin materials. Through LCA procedure, a holistic methodology is employed in iCAREPLAST to calculate the true impact of chemical recycling. With this system perspective, the user can be assisted in decision-making regarding the environmental impacts of recycling process. LCA can be further extended to live LCA. In this, dynamic LCA does real-time calculation based on continuously acquired data from pilot plant. The present system's state of the recycling process in terms of impacts is very advantageous in automating decision-making through optimization techniques. In conclusion, understanding the benefits of material efficiency and life cycle perspective is key to reducing environmental burden of new and upcoming recycling technologies. Also, the integration of LCA and process optimization in these recycling processes is a vital aspect to generate meaningful insights on the environmental burdens.